Let's start with what's actually true, because there's a real, well-documented, genuinely remarkable event hiding underneath this headline, and then there's an invented layer stacked on top of it that didn't happen. In December of 2024, in Santa Barbara, California, Google's quantum computing team unveiled a new processor called Willow, and it did, in fact, complete a specific computation in under 5 minutes that the company estimated would take today's fastest classical supercomputer approximately 10 septillion years. A number so large, it exceeds every meaningful timescale in physics, roughly a quadrillion times longer than the age of the universe itself. That part is real, published in the peer-reviewed journal Nature, confirmed by Reuters and other mainstream outlets, and openly discussed by Hartmut Nevin, the head of Google Quantum AI, in on-the-record interviews. What's not real is the specific claim that Willow found something it wasn't supposed to, a phrase that, once you go looking for its source, traces back to nothing more than a cluster of recycled videos, several of which have added their own increasingly dramatic flourishes on top of the same basic, real announcement. One particularly elaborate version even invents a quote from a supposed Nobel laureate physicist named Dr. Elias Raskin, describing a mysterious shutdown at a closed-door symposium in Zurich. There is no verifiable Nobel laureate by that name in physics, no record of that symposium, and no other independent source anywhere reporting on it. That's not a suppressed story. That's a fabricated character, invented specifically to make an unsourced claim sound like it came from a credible authority. So let's do this properly. Let's walk through exactly what Willow really did, why it's genuinely one of the more significant developments in modern computing, even without any invented mystery attached. And then let's talk honestly about why headlines like this one keep getting built around real quantum computing news in the first place, because understanding that pattern is arguably more useful to you long-term than any single debunking. Willow is a superconducting quantum processor, built from 105 qubits, the quantum equivalent of the bits inside your laptop, except instead of being firmly 0 or 1, a qubit can exist in a superposition, a blend of both possibilities simultaneously, right up until it's measured. To keep those fragile quantum states intact, Willow operates inside a specialized refrigerator cooled to a temperature colder than the emptiest regions of outer space, since even the faintest trace of ordinary heat is enough to instantly disrupt the delicate quantum behavior the whole chip depends on. This is standard, well-understood physics, the same basic approach Google has used since its earlier Sycamore chip, and the same general hardware philosophy other leading labs, including IBM and China's Zhuangzi program, have pursued as well. The specific benchmark Willow completed is called random circuit sampling, a computational task deliberately chosen because it plays to quantum computing's greatest strength while being almost impossibly hard for a classical computer to simulate directly. It works by running an intricate, carefully structured sequence of quantum operations across all 105 qubits, and then measuring the resulting pattern of outcomes, a calculation that requires tracking an astronomically large space of possible quantum states, a space that grows exponentially larger with every additional qubit you add to the system. This exponential growth is exactly why the classical comparison numbers get so extreme so quickly. It's not a marketing exaggeration, it's simply what happens mathematically once you're tracking that many interacting quantum possibilities at once. And it's precisely the kind of task where quantum hardware's fundamental design gives it a genuine, verifiable, structural advantage over any classical computer, however powerful. It's worth being fair and complete here and mentioning the part of this story that responsible reporting always includes alongside the impressive headline number, because it's exactly the kind of detail a fabricated video tends to leave out. Google made a similar supremacy claim back in 2019 with its earlier Sycamore chip, stating a specific benchmark task would take a classical supercomputer around 10,000 years to replicate. IBM researchers pushed back directly and publicly, arguing that with more sophisticated classical simulation techniques, the same task could actually be completed in about 2.5 days, a vastly smaller gap than Google's original estimate. That's a real, healthy, entirely normal example of how legitimate scientific claims get tested, challenged, and refined by other qualified researchers, with every incentive to find flaws in a rival's math. It's also exactly the opposite of what a fabricated video implies when it claims a shadowy, unexplained shutdown happened behind closed doors with no outside scrutiny at all. Real quantum computing claims get argued over in public, with names attached in journals anyone can read. Beyond the raw speed benchmark, Willow's announcement included something arguably more technically significant, and definitely more important for the field's long-term future, a genuine breakthrough in quantum error correction. Quantum computers have always faced a brutal, self-defeating problem. Qubits are extraordinarily fragile, easily disrupted by heat, stray radiation, or even a passing cosmic ray, and for years, the more qubits you added to build a more powerful machine, the more errors you accumulated, making the whole system less reliable rather than more. Willow demonstrated, for the first time with solid experimental backing, that this didn't have to be true. By linking qubits together using a specific error-correcting scheme called a surface code, the Google team showed that as they added more physical qubits to protect a single, more robust logical qubit, the error rate actually dropped exponentially rather than climbing. That's a milestone quantum computing researchers had been chasing since a foundational 1995 theoretical proposal first suggested it should be possible, and Willow was the first system to demonstrate it clearly, with the error rate improving in a clean, predictable pattern exactly matching the decades-old theory. Nevin's own summary of the moment, delivered in an on-the-record interview rather than a leaked, unverifiable quote, was refreshingly plain. "We are past the break-even point. A real, quotable, checkable statement from a named person, exactly the kind of detail that's conspicuously absent from every fabricated version of this story. There's also a real, genuinely debated scientific controversy tied to this same Willow announcement. And it's worth including here precisely because it shows you what an authentic, contested claim about this chip actually looks like, in contrast to the invented something it wasn't supposed to find framing." In that same December 2024 announcement, Nevin wrote that Willow's extraordinary performance lends credence to the notion that quantum computation occurs in many parallel universes, directly referencing physicist David Deutsch's many worlds interpretation of quantum mechanics, a real, decades-old, seriously debated position within physics, though very much a minority one. Plenty of physicists pushed back on that framing directly and publicly, pointing out that the far more mainstream Copenhagen interpretation explains exactly the same underlying mathematics, the same quantum interference effects that make Willow's speed possible, without needing to invoke any parallel universes at all. Both interpretations predict the exact same measurable outcome, which is precisely why this remains a genuinely open philosophical debate, rather than something Willow's raw performance could resolve either way. That's real scientific disagreement conducted by named researchers, in public, over a specific quotable claim, and it's a perfect example of how strange and legitimately debatable actual quantum computing news can be, without anyone needing to invent a mysterious shutdown or an anonymous, unverifiable expert to make the story feel important. Now, here's where I want to spend real time on something useful. Because if you've clicked on more than one video with a title like this one, you've probably noticed they tend to follow an oddly similar shape, and recognizing that shape is genuinely valuable, well beyond just this single headline. Nearly every version of this fabricated Willow story follows the same basic structure. Start with the one real verifiable detail. Willow completed its benchmark in under 5 minutes, then immediately pivot to a vague, dramatic claim with no specific source attached. Something was found, something wasn't supposed to happen, a shutdown occurred, engineers were alarmed. Notice what's consistently missing from that pivot. A specific date, a specific named researcher who's actually verifiable, a link to any published paper or any statement from Google itself confirming the dramatic part of the story. The real, verified detail always comes with all of that supporting evidence attached. The invented part never does, and once you start looking for that gap specifically, whether it's a missing citation, an unverifiable name, or a claim that no other outlet anywhere is independently reporting, these videos become dramatically easier to spot for what they are, regardless of which company or which scientific field they happen to be built around this time. It's worth understanding why this particular story, quantum computing chips supposedly discovering something they shouldn't, keeps proving to be such fertile ground for this kind of fabrication, because the appeal isn't random. It comes from a real, understandable place. Quantum mechanics genuinely is strange, genuinely does defy ordinary intuition, particles existing in multiple states at once, measurement changing outcomes, entanglement linking particles instantaneously across any distance, and Willow's actual real performance numbers are already so far outside normal human experience, a quadrillion times the age of the universe, that the leap to, and then it found something impossible, doesn't feel as implausible to someone without a physics background as it should. The genuine science is weird enough that an invented embellishment slides in easily, wrapped in the credibility of a real company and a real verified headline number, which is exactly the recipe that makes this kind of content spread so effectively, and exactly why it's worth being a little more skeptical the more dramatic and vague a follow-up claim gets. Let's also talk honestly about why a fabricated authority figure like the Nobel laureate Dr. Elias Raskin shows up in some of these videos specifically, because it's a technique worth recognizing on its own. Inventing a credentialed sounding expert, attaching a prestigious title, Nobel laureate, a specialized sounding field, quantum field theory and nonlinear time models, and a vague, unverifiable setting, a closed-door symposium, leaked to the media, creates the appearance of authoritative sourcing without any of the actual accountability real sourcing requires. A real Nobel laureate physicist commenting on Willow would be a genuinely newsworthy event covered by physics publications, university press offices, and mainstream science journalists, none of whom have ever reported on this person or the symposium, because neither appears to exist. This is worth remembering well beyond this one video, because inventing a fake expert with an impressive sounding title is one of the single most common techniques used across manufactured science content generally, precisely because most people, reasonably, don't have the time or the specialized knowledge to verify every credential attached to every quote they come across. So let's bring this back to what actually deserves your attention, because the honest version of this story really doesn't need any of that invented material to be worth your time. Willow's real published performance represents a genuine hard-won engineering achievement, crossing a fault tolerance threshold that quantum computing researchers had been chasing since the 1990s, while simultaneously demonstrating a computational speed advantage over classical computers so large that ordinary numbers barely capture it. That achievement immediately generated real, substantive scientific debate, echoing the exact same kind of scrutiny Google's earlier Sycamore claims received from IBM back in 2019. And it reopened a genuinely serious 70-year-old philosophical argument among physicists about what quantum mechanics actually implies about the nature of reality itself. None of that required a mysterious shutdown, an unnamed expert, or a closed-door symposium in Zurich to be significant. It was significant on its own, published in a real journal, discussed by real, named scientists, and debated openly and publicly exactly the way legitimate scientific claims are supposed to be tested. If you take one thing away from this, let it be a simple, durable habit, rather than just the specific facts about this one chip. The next time you see a headline claiming some company's cutting-edge technology found something it wasn't supposed to, or discovered something scientists refuse to explain, pause for just long enough to ask a few basic questions. Is there a specific date attached to this claim? A specific named person you can actually verify exists and holds the credentials attributed to them? A link to a published paper, or at minimum, independent coverage from more than one outlet reporting the same specific detail? If those things are present, you're likely looking at real, if perhaps dramatically framed science, the same kind of legitimate story Willow's actual benchmark and error correction results represent. If those things are entirely absent, replaced instead by vague phrasing, unnamed sources, and a dramatic but conveniently unfalsifiable central claim, you're very likely looking at exactly what this specific video turned out to be: a real, genuinely impressive scientific achievement, borrowed as a credible-sounding backdrop for a story that never actually happened. Let's spend some more time with the actual mechanics of what makes Willow's error correction breakthrough so significant, because it's genuinely one of the more important quantum computing milestones of the past several years, and it deserves a fuller explanation than a single paragraph can give it. Every physical qubit in a quantum processor is inherently noisy and error-prone, subject to disruption from heat, electromagnetic interference, and even the occasional cosmic ray passing through the chip. For decades, the standard solution proposed by theorists was something called a surface code, a scheme that takes many individually unreliable physical qubits and weaves them together into a single, much more robust logical qubit, using a lattice-like arrangement where some qubits store information and others continuously check their neighbors for signs of error without ever directly reading the protected information itself, since directly reading a qubit would collapse its fragile quantum state and destroy the very information being protected. The theory, dating back to a 1995 proposal, predicted that if your physical qubits were good enough, meaning their individual error rates were low enough to sit below a specific calculable threshold, then adding more of them to this correcting lattice should make your logical qubit's reliability improve exponentially. The larger the lattice, the better the protection. Below that threshold, more qubits helps. Above it, more qubits actively hurts, adding more moving parts and more chances for something to go wrong. For 30 years, this threshold existed mostly on paper, a beautiful piece of math nobody had cleanly, unambiguously demonstrated in a working system. Willow changed that, showing a real logical error rate that dropped in a clean, predictable curve as researchers increased the size of the correcting lattice, exactly matching what the decades-old theory predicted. That's the actual something. This real experiment found not a mysterious anomaly, but a confirmation, delivered with hard experimental data, that a 30-year-old theoretical promise about how to scale quantum computers actually holds up in reality. It's worth pausing on why that particular achievement matters more in a practical sense than the flashier 10 septillion year speed comparison that tends to dominate headlines. A single, narrow speed benchmark, however dramatic, doesn't by itself tell you whether quantum computers can be reliably scaled up to solve broader, more practically useful problems. The error correction result does exactly that, because it addresses the core reason quantum computing has taken so long to move from laboratory curiosity toward genuinely useful, general-purpose technology. Without a working solution to the scaling versus reliability trade-off, Building bigger quantum computers was, for decades, a losing battle, adding qubits while simultaneously adding errors faster than you could correct them. Willow's demonstration that this trade-off can be beaten with real verified, exponentially improving results as the correcting lattice grows is arguably the single most important piece of this entire announcement, even though it gets far less attention in viral headlines than the more visually dramatic speed comparison, and considerably less attention than the entirely invented something it wasn't supposed to find storyline built on top of it. There's also real value in walking through, one more time and in a bit more depth, exactly why the premise of a quantum chip finding something impossible, or being abruptly shut down after an unexplained discovery, runs into trouble on basic physics grounds. Because this specific detail comes up across multiple versions of the fabricated story, and it's worth debunking thoroughly, rather than just once in passing. A quantum processor like Willow doesn't operate the way popular fiction sometimes imagines an artificial intelligence operating, exploring, noticing things, reacting with alarm. It runs a specific, pre-designed sequence of quantum logic operations, a circuit, on its qubits. And then researchers measure the result, comparing the actual measured outcome against what quantum theory predicts should happen. There is no mechanism inside this process for the chip to notice something outside its programmed calculation, flag it as unusual, or trigger some kind of automatic shutdown in response to an unexpected result, the way a smoke detector might trigger an alarm. If a measurement outcome didn't match theoretical predictions, that would show up simply as a discrepancy in the data, something researchers would then investigate through entirely ordinary scientific means, checking for equipment calibration issues, environmental interference, or genuine new physics, exactly the same unglamorous, methodical process used to investigate any unexpected result in any physics experiment, published and argued over through completely normal traceable scientific channels rather than a leaked account of a closed-door symposium. It's also worth noting that Google's quantum computing announcements, including the Willow reveal, have consistently been unusually open and detailed by the standards of corporate technology announcements generally. The company published its error correction results in Nature, one of the most rigorously peer-reviewed scientific journals in the world, a process that requires independent expert reviewers to scrutinize the methodology, the data, and the conclusions before publication, specifically to catch exactly the kind of overstated or unsupported claim a fabricated video would have you believe Google was trying to hide. Nevin himself gave on-the-record interviews to Reuters and other established news organizations, answering direct questions about the results, a world apart from the pattern of vague, unnamed, unverifiable sourcing that runs through every fabricated version of this story. When you compare those two patterns side by side, one full of names, journals, dates, and on-record quotes, the other full of vague symposiums, anonymous alarm, and invented Nobel laureates, the difference in credibility isn't subtle. It's about as clear a contrast between real reporting and manufactured content as you're likely to find in any single comparison. There's a broader pattern here worth naming plainly, because it connects this specific fabricated Willow story to a whole recurring genre of similar content that keeps attaching itself to real, legitimate quantum computing news. Google's actual quantum computing program has generated a steady stream of genuinely fascinating, well-documented results over the past several years. The original 2019 Sycamore supremacy claim, and the real scientific pushback it received from IBM. The 2024 Willow error correction and speed benchmark results we've just walked through in detail. Nevin's genuinely controversial multiverse comment that reopened a decades-old physics debate, and a 2025 follow-up experiment called Quantum Echoes that gave physicists a real, controlled window into information-scrambling physics connected to black holes and the earliest moments of the universe. Every one of those stories is real, verifiable, and genuinely strange enough to be worth your attention entirely on its own honest merits. And every single one of them has, at some point, been recycled into a fabricated video claiming something considerably more dramatic and considerably less true, a scientist silenced, a discovery suppressed, a shutdown nobody can fully explain. Recognizing that this specific pattern, real breakthrough plus invented dramatic layer, keeps repeating across Google's quantum computing coverage, specifically, is genuinely useful information, because it means the next headline in this exact style, whatever specific claim it makes, deserves the same careful, skeptical treatment we've just given this one. So here's where that leaves us, and it's a genuinely satisfying place to land precisely because it doesn't require choosing between boring skepticism and exciting science. Willow really did complete a calculation in under 5 minutes that would take a classical supercomputer longer than the age of the universe to replicate. It really did cross a 30-year-old theoretical threshold in quantum error correction, verified through peer review, and confirmed in on-record statements from named researchers. Its results really did reignite a genuine, serious, decades-old philosophical debate among physicists about the fundamental nature of reality. None of that needed embellishment to be worth talking about, and none of it needed an invented Nobel laureate, a fictional Zurich symposium, or a mysterious, unexplained shutdown to earn your attention. The real story was always strange enough on its own, and now that you've heard both versions side by side, you're in a considerably stronger position to spot the difference. The next time a similarly dramatic headline about this same chip, or the next one after it, shows up in your feed. It's worth adding a little more context on how Willow actually fits into the broader competitive landscape of quantum computing, because that context tends to get lost entirely when a story gets flattened down into a single dramatic claim about a shutdown or a forbidden discovery. Google isn't operating in isolation here. IBM has its own aggressive quantum computing roadmap, with processors like Condor pushing past 1,000 physical qubits, prioritizing a somewhat different strategy focused on scaling raw qubit count alongside its own error mitigation techniques. China's Zhuangzi program, based at the University of Science and Technology of China, has pursued a broadly similar path to Google's, using superconducting qubits and, in late 2025, announcing its own below-threshold error correction milestone using a different control architecture than Google's approach, an independent confirmation that this general class of error-correcting breakthrough isn't a fluke specific to one lab's particular hardware quirks. Quantinuum, working with a different qubit technology entirely based on trapped ions rather than superconducting circuits, has also posted its own random circuit sampling results, adding yet another independent data point to the broader picture of how quickly this field is genuinely advancing across multiple competing technical approaches. None of this competitive landscape gets mentioned in the fabricated something it wasn't supposed to find videos, because acknowledging a broader, well-documented multi-company scientific race doesn't fit neatly into a story built around a single, isolated, unverifiable incident. But it's exactly this broader, competitive, independently verified context that makes Willow's real achievement credible in the first place. One genuine result among several converging lines of evidence from multiple serious labs, rather than one isolated, unconfirmed claim from a single source with no outside scrutiny at all. There's also something worth saying about how you, as a viewer, can actually get more genuine enjoyment out of following real quantum computing news. Once you've learned to filter out the fabricated layer built on top of it, the real story, followed honestly over the past several years, is already a genuinely gripping, ongoing narrative. Sycamore's 2019 claim, and IBM's immediate, well-reasoned challenge to it, Willow's 2024 error correction breakthrough and its accompanying multiverse controversy, China's parallel and competing error correction milestone in 2025, and the Quantum Echoes experiment that same year, giving physicists their first real experimental foothold on questions about information and chaos that used to belong entirely to theoretical black hole physics. That's a rich, multi-year, multi-company, scientifically substantive story with real disagreements, real stakes, and real open questions still being actively worked out by named researchers and published papers. You can actually go read yourself if you're curious. Following that real story doesn't require any invented drama to stay interesting, and honestly, once you start tracking it directly, rather than through a chain of recycled, increasingly exaggerated secondhand videos, it tends to become more engaging, not less, because you're following an actual unfolding scientific competition with real winners, real setbacks, and real stakes, rather than a single manufactured mystery with a conveniently vague, unfalsifiable ending. And that, in the end, might be the most useful takeaway to carry forward from this specific video and its many recycled cousins. The real Willow story earned its place in serious science journalism, in a peer-reviewed journal, and in on-record statements from named researchers, entirely on its own merits, no embellishment required. The fabricated version needed an invented Nobel laureate and an unverifiable closed-door symposium to feel important, because without those additions, there simply wasn't anything there. That contrast between a story so genuinely remarkable it didn't need to be exaggerated and a story so empty it had to invent its own expert witness tells you almost everything you need to know about which version actually deserves your trust.